From far out in space, our planet looks like a small blue marble hanging in the dark. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That blue color comes mostly from water. Oceans cover about 70% of Earth's surface, and from a distance, they seem perfectly still and calm, but they are not still at all. Right now, as you listen to this, the oceans are moving. They rise and fall along every coastline on Earth. Water that was lapping at the base of a cliff this morning may be sitting 30 feet higher by afternoon, and then, just as quietly, it will pull back again. This happens every single day, in every ocean, on every shore. It has been happening for billions of years. Something is pulling that water. Something far away. Something you cannot see or feel from where you are lying right now. And yet its grip on our planet is real and steady and ancient. That something is the moon. The moon sits about 239,000 miles from Earth. That is a vast distance. If you could drive a car at highway speed without stopping, it would take you more than 5 months to get there. And yet, across all that empty space, the moon reaches out with its gravity and tugs on our oceans. It stretches them. It pulls the water on the side of Earth closest to it slightly toward the sky. The result is a slow, enormous swelling of the sea that we call a tidal bulge. This is the force we are going to spend our time with tonight. Tidal force. It is one of the quietest and most powerful forces shaping the world around you. Tidal forces are not unique to Earth. They are one of the great organizing forces of the entire solar system. They sculpt moons, crack the surfaces of distant worlds, heat the interiors of icy bodies far from the sun, and even pull galaxies apart over billions of years. What begins as a gentle rise and fall of water on a beach connects outward to some of the most dramatic events in the cosmos. But here, on this small blue world, the effects are close enough to touch. Stand on a beach at low tide. The wet sand stretches out before you, dark and smooth. Tide pools sit in the rocks, full of small creatures waiting for the water to return. The air smells like salt and cold stone. Then come back 6 hours later. The water has climbed. Those rocks are submerged. The sand is gone. The moon did that. It did it without making a sound. The tides have shaped our coastlines over millions of years. They have carved sea caves and sea arches. They have built tidal flats and salt marshes. They have created the rich, wet zones between land and sea, where some of the earliest complex life on Earth may have taken its first steps. The rhythm of the tides is woven into the biology of countless creatures: crabs, clams, sea stars, and hundreds of species of fish all time their feeding, their breeding, and their movement to the rise and fall of the water. Even the length of our day is connected to the tides. The moon's pull creates a kind of friction as it drags the oceans across the spinning earth. That friction is slowly, very slowly, putting the brakes on our planet's rotation. Earth's days are getting longer, not by much. About 2 milliseconds every 100 years. But over billions of years, that adds up. Long ago, a day on Earth was only about 6 hours long. The tides have been stretching it out ever since, and the moon itself is drifting away because of this same process. Every year, it moves about 1.5 inches farther from Earth. That is roughly the same rate your fingernails grow. Slow, quiet, steady. Everything is connected. The water on your nearest shore, the moon hanging in the dark sky, the length of your day, the creatures living in the rocks at the water's edge, all of it tied together by this one invisible force. Tonight, we are going to follow that force. We will start here on Earth with the basics of how tides work. Then we will move outward past the moon, past the outer planets, all the way to the edges of galaxies. We will see what tidal forces do when they are gentle, and what they do when they are not. For now, just breathe. The tide is coming in. Gravity is the great organizer of the universe. It holds stars together. It keeps planets in their paths. And here on Earth, it pulls the ocean water toward the moon in a slow, steady rhythm that never stops. But tidal forces are not quite the same thing as plain gravity. They are something more specific. To understand them, picture this. The moon is pulling on Earth, but Earth is not a single point. It has a near side and a far side. The near side of Earth is closer to the moon, so the moon's gravity pulls on it a little harder. The far side is farther away, so the moon's gravity pulls on it a little less. That difference in pull across the width of our planet is what we call a tidal force. It is the stretch, the uneven tug, the way gravity pulls harder on one side than the other. Think of it like this. Imagine you are holding a rubber band with both hands. If someone pulls on one end harder than the other, the rubber band stretches. That is what the moon does to Earth. It pulls harder on the side facing it, and less hard on the side facing away. The result is a gentle stretching of everything on our planet, including the ocean. The moon is about 239,000 miles away from Earth. That is roughly the distance you would travel if you drove a car around the planet Earth about 9.5 times. It is far, but the moon is also quite large. Its diameter is about 2,100 miles across. That is roughly the width of the continental United States from coast to coast. Something that big at that distance still has a real and measurable pull on everything here. The moon's mass, meaning the amount of matter packed into it, is about 1% of Earth's mass. It is much smaller than our planet. But mass is not the only thing that matters when it comes to tidal forces. Distance matters enormously. The closer an object is, the stronger its tidal pull. Even a smaller object nearby can create a stronger tidal force than a larger object far away. This is why the moon, not the sun, is the main driver of Earth's tides. The sun is about 27 million times more massive than the moon. That is an almost impossible number to picture. But the sun is also about 93 million miles away. The moon is only about 239,000 miles away. Because tidal force depends so strongly on distance, the moon's closeness wins. The moon creates a tidal force on Earth that is about 2.5 times stronger than the sun's. The math behind this is elegant. Tidal force does not just shrink as distance grows. It shrinks much faster than that. Scientists describe this by saying tidal force falls off with the cube of the distance. That means if you double the distance between two objects, the tidal force between them drops to 1/8 of what it was. Not 1/2, 1/8. Distance matters more than almost anything else. This is why tidal forces are so important in the universe. They are strongest between objects that are close together, and they can be gentle, like the moon's pull on our ocean, or they can be violent when objects get very close to something far more massive than themselves. On Earth, the tidal force we feel is soft. It moves water. It bends the ground very slightly. It does its work quietly over long stretches of time. The ocean responds to it because water is free to flow. The ground responds too, though you would never feel it. The solid rock of Earth's crust rises and falls by a few inches twice a day, pulled by the same force that moves the sea. That is one of the quiet wonders of tidal forces. They do not just act on the surface, they act on everything. Every layer of our planet feels that uneven pull. The ocean shows it most clearly because water moves so easily. But the rock beneath your feet is breathing too, in its own slow and nearly invisible way. So when you watch the tide come in, you are watching the result of a force that stretches across nearly 250,000 miles of empty space. A force born from the simple fact that the near side of Earth is closer to the moon than the far side. A difference in pull. A stretch, quiet, steady, and ancient. This is what a tidal force is. And now that we know what it is, we can begin to understand what it does. To understand what tidal forces do, it helps to know where they came from. The story begins about 4.5 billion years ago, when our solar system was nothing but a vast spinning cloud of gas and dust. That cloud slowly pulled itself together under its own gravity. The sun formed at the center, and around it, smaller clumps of rock and metal began to gather and grow. Earth was one of those growing worlds. It was young and violent then. Nothing like the calm blue planet we know today. The surface was covered in molten rock, and the sky was thick with heat and debris. Space was crowded in those early years, and collisions between young planets and large rocky bodies were common. Then, roughly 4.5 billion years ago, something enormous happened. A body about the size of Mars came crashing into the young Earth. Scientists call this object Theia. The collision was not a gentle one. It was catastrophic. The impact threw an enormous cloud of vaporized rock and molten debris out into space around Earth. That debris did not drift away. Earth's gravity held it close. And over time, perhaps just a few thousand years, that cloud of shattered rock slowly gathered itself together. It clumped and cooled and grew. And from that wreckage, the moon was born. This is called the giant impact hypothesis, and it is the leading scientific explanation for how the moon formed. The evidence for it is strong. The moon's rock is chemically very similar to Earth's outer layers. It has almost no iron core, which makes sense if it formed from the lighter material blasted off Earth's surface. And the moon is unusually large compared to Earth. Most moons in our solar system are tiny compared to their parent planets. Ours is not. It is enormous, relatively speaking, and that size is part of what makes its gravitational pull so powerful from where we stand. When the moon first formed, it was much closer to Earth than it is today. Scientists believe it may have sat as close as 15,000 miles away. At that distance, the tidal forces it created would have been almost unimaginably strong. The oceans of early Earth, if any existed yet, would have been pulled into waves of tremendous height. The solid ground itself would have flexed and bent far more than it does now. The young Earth and its new moon were locked in an intense gravitational embrace, but the moon did not stay that close. Even from the very beginning, tidal forces were slowly pushing it away. This is one of the quiet ironies of the moon's story. The same force that the moon exerts on Earth also acts in reverse. Earth's gravity tugs on the moon, and because Earth spins faster than the moon orbits, the tidal bulge that the moon raises in Earth's oceans actually sits slightly ahead of the moon in its orbit. That bulge pulls the moon forward, like a gentle hand nudging it along. Over billions of years, that nudge has added energy to the moon's orbit and pushed it gradually outward. The moon has been drifting away from Earth ever since it formed. Today, it sits about 239,000 miles away, and it is still moving outward at a of about 1.5 inches per year. That is roughly the same speed at which your fingernails grow. Slow, steady, and continuous. So the moon we see tonight is not the moon that ancient Earth once knew. It is farther away. It pulls a little less strongly than it once did. And the tides it creates are gentler than the towering walls of water that may have swept across the young planet long ago. What is remarkable is that even across that vast and growing distance, the moon still moves our oceans. It still lifts the sea twice a day. It still makes the ground beneath your feet rise and fall by a few inches. That pull has never stopped. It has only softened slowly over billions of years. The moon formed from violence, from a collision so massive it reshaped our entire planet. And out of that destruction came something that has shaped life on Earth in ways we are still discovering. The rhythm of the tides, the stability of our seasons, the slow turning of our days, all of it traces back to that ancient impact, to the debris that gathered in the dark, and to the quiet, steady pull that has connected Earth and moon ever since. It is a bond forged in fire, and it has lasted 4.5 billion years. So the moon pulls on Earth. We know that now. But the way it pulls creates something surprising. Something that took scientists a long time to fully understand. The ocean does not simply rise on the side of Earth facing the moon and stay flat everywhere else. It rises on both sides at once. Two bulges of water form at the same time on opposite ends of the planet. And that is why, in most places on Earth, high tide comes twice a day. Here is how it works. The moon's gravity pulls on everything it faces. It pulls on the ocean water closest to it most strongly. That water gets tugged toward the moon, and it piles up. It forms a bulge. A gentle, enormous dome of water stretching across the ocean surface on the side of Earth nearest the moon. That part makes sense to most people. But then there is the second bulge, on the far side of Earth, pointing away from the moon entirely. That one feels like a mystery. The answer lives in the difference between forces. The moon pulls on the near side of Earth more strongly than it pulls on Earth's center, and it pulls on Earth's center more strongly than it pulls on the far side. This difference in pull is what scientists call a tidal force. The water on the far side of Earth is being pulled toward the moon less strongly than the solid ground beneath it. So that water gets left behind. It lags, and in lagging, it forms its own bulge, stretching outward away from the moon like the trailing edge of something being dragged forward. Think of it this way. Imagine holding a soft ball and pulling one side of it toward you. The near side stretches toward your hand, but the far side stretches away because the middle of the ball is being pulled more than the far edge. The ball elongates. Earth's oceans do the same thing. They stretch into an oval shape, with one bulge pointing toward the moon and one pointing away. Earth rotates inside these two bulges. As our planet spins, different parts of the ocean pass through the near side bulge. And then, roughly 12 hours later, through the far side bulge. Each time a coastline passes through one of these bulges, the water rises. High tide arrives. Then Earth keeps turning. The coastline moves out of the bulge, and the water falls back. Low tide settles in. Then the cycle repeats. 2 high tides, 2 low tides, roughly every 24 hours and 50 minutes, which is how long it takes for the moon to appear in the same spot in the sky again as Earth spins. That extra 50 minutes matters. It means high tide does not arrive at the same clock time every day. It shifts. It slides forward by about 50 minutes each day, following the moon as the moon slowly orbits Earth. Coastal communities have tracked this pattern for thousands of years. Fishermen read it. Sailors depended on it. Ancient peoples built their lives around it. The rhythm was always there, steady and reliable, even before anyone understood why. The shape of the coastline changes how strongly the tides are felt. In the open ocean, the difference between high tide and low tide might be less than 2 feet. But where the ocean is forced into a narrowing bay or a shallow channel, the water has nowhere to spread. It piles up. The tidal range grows enormous. The Bay of Fundy in eastern Canada is the most dramatic example on Earth. There, the shape of the bay acts almost like a funnel. The water rushes in and has no room to escape. The tidal range in the Bay of Fundy can reach over 50 feet. That is a 5-story building's worth of ocean rising and falling twice a day. The same moon, the same two bulges, but the land shapes the water into something extraordinary. And yet, even in the open ocean, far from any coast, those two bulges are always there, moving, quiet, invisible from the surface, but real in every measurement. The ocean is never truly still. It breathes in and out on a rhythm set by a world 250,000 miles away. What is worth sitting with is how simple the cause is, and how complex the effects become. Two bulges of water, stretched by a difference in gravity across the width of a planet. That is the whole mechanism, and from that simple stretching comes the rise and fall of every tide on Earth, the carving of every tidal coastline, the rhythm that living things have followed for hundreds of millions of years. The moon does not touch the ocean. It only pulls, and that pull is enough to move the sea. But the moon is not alone in this work. 93 million miles away, the sun is pulling on Earth too. Its gravity reaches across that vast distance and touches every ocean, every lake, every drop of water on this planet. The sun is enormous. It holds more than 99% of all the mass in the solar system. Its gravity is powerful beyond easy imagining. And yet, when it comes to raising tides, the sun plays a quieter role than the moon. This surprises most people when they first hear it. The sun is about 27 million times more massive than the moon. Its total gravitational pull on Earth is much stronger, but tidal forces do not depend only on how strong gravity is. They depend on how much gravity changes across a distance. That difference from one side of Earth to the other is what creates the stretching. And because the sun is so far away, its gravity changes very gently across the width of our planet. The moon is close. Its gravity changes steeply across that same distance. Steepness is what matters here. Scientists calculate that the sun's tidal force on Earth is about 46% as strong as the moon's, less than half. The moon wins this quiet contest, not because it is bigger or heavier, but because it is near. Closeness in the world of tidal forces is everything. So the sun creates its own pair of tidal bulges in Earth's oceans, are smaller than the moon's bulges, but they are real. They follow the sun as Earth turns, just as the moon's bulges follow the moon. Two sets of bulges moving across the ocean at once, each one driven by a different source of gravity. The ocean is responding to both of them at the same time, every hour of every day. This is where things become layered and interesting. When the sun and the moon pull in the same direction, their bulges add together. The ocean gets stretched a little more than usual. Tides rise higher. Tides fall lower. The difference between high and low water grows. When the sun and the moon pull at angles to each other, their effects partly cancel out. The tides become more moderate, smaller, quieter. The sun's position in the sky changes slowly over the course of a year. Earth orbits the sun, completing one full loop every 365 days. As Earth moves through that orbit, the angle between the sun and the moon shifts constantly. Some days they are nearly aligned. Some days they are nearly at right angles. The tides feel every one of those changes. There is something worth pausing on here. The sun is so far away that its light takes about 8 minutes to reach us. 8 minutes of travel, even at the speed of light. And yet its gravity, moving at that same speed, reaches across that distance and gently lifts the ocean, not by much, but by enough to matter. The sun's tidal contribution is woven into every tide chart ever written. Earth also has a slightly oval-shaped orbit around the sun. It is not a perfect circle. In early January, Earth reaches its closest point to the sun, a position called perihelion. At that point, Earth is about 3 million miles closer to the sun than it is in early July. 3 million miles sounds large. Compared to 93 million, it is a modest difference, but it is enough to make the sun's tidal pull slightly stronger in January than in July. The tides in winter are, on average, just a little more influenced by the sun than the tides in summer. These are small effects, but the ocean notices. The ocean notices everything. What is worth sitting with is how the sun and moon are in constant, slow conversation with each other through the medium of Earth's oceans. Neither one acts alone. The moon pulls. The sun pulls. Earth spins through both of those poles at once. The water responds to the combined effect of two different worlds, one close and one impossibly far, both reaching down and touching the sea. The sun does not dominate the tides, but it shapes them. It modifies them. It adds its voice to a process that would exist without it. And in doing so, it changes the rhythm. The tides we experience are not purely the moon's work. They are a shared creation, written in water, across a distance that is almost too large to hold in the mind. And that shared creation changes its character depending on where the sun and moon stand relative to each other, which is exactly where we are headed next. So the position of the sun and moon relative to each other is everything. It changes the character of the tides in ways you can measure, ways you can see, ways you can feel if you stand at the edge of the water and pay close attention over the course of a month. There are two kinds of tidal patterns that repeat on a regular cycle. One is called a spring tide. The other is called a neap tide. These two patterns are not random. They follow a precise schedule, tied directly to the phases of the moon. Spring tides have nothing to do with the season of spring. The name comes from an old word meaning to leap or to surge. A spring tide happens when the sun, the earth, and the moon line up together. This occurs twice a month, once at the new moon and once at the full moon. At the new moon, the moon sits between the earth and the sun. At the full moon, the earth sits between the moon and the sun. In both cases, the three bodies form a straight line, and when that line forms, the gravitational pulls of the sun and moon combine. They add together. They reinforce each other. The result is a tide that is noticeably stronger than usual. The high tides during a spring tide are higher than average. The low tides are lower than average. The difference between the two, what scientists call the tidal range, grows. Along a coastline that normally sees a modest tide, a spring tide can push the water noticeably further up the beach. In places where tides are already dramatic, a spring tide can be extraordinary. Think of it this way. Imagine two people pulling a rope in the same direction. Their combined strength is greater than either one alone. That is a spring tide. The moon and sun are not touching the ocean with hands, of course, but their gravity reaches across space and pulls the water in the same direction at the same time, and the ocean responds. Neap tides are the opposite. They happen when the sun and moon are at right angles to each other, as seen from Earth. This occurs at the first quarter moon and the third quarter moon, roughly 1 week after each new or full moon. At these moments, the sun and moon are pulling the ocean from different directions. Their pulls do not add together. They partially cancel each other out. The result is a tide that is weaker than average. The high tides are not as high. The low tides are not as low. The tidal range shrinks. Picture those same two people now pulling the rope from different sides, each one working against the other's effort. Neither one wins completely. The rope barely moves. That is a neap tide. The ocean still rises and falls because the moon's pull is still dominant, but the range is reduced. The water is quieter. The tides are gentler. The difference between spring and neap tides is significant. In many coastal areas, the tidal range during a spring tide can be roughly 50% greater than during a neap tide. In some locations, that difference is even more dramatic. The Bay of Fundy on the eastern coast of Canada holds the record for the highest tides on Earth. During a spring tide, the water there can rise more than 16 meters, which is taller than a 5-story building. The same bay during a neap tide sees a noticeably smaller rise. The bay's shape amplifies the effect, acting almost like a funnel that concentrates the tidal energy, but the underlying cause is always the same: the alignment of the sun and moon. This cycle of spring and neap tides repeats roughly every 2 weeks, following the moon's phases with quiet precision. It has been repeating for billions of years. Long before any human stood at a shoreline and noticed the water rising, this rhythm was already running. The moon was already pulling. The sun was already adding or subtracting its voice. The ocean was already responding. What is remarkable is how predictable it all is. Astronomers and oceanographers can calculate the timing and height of tides' years, even centuries, in advance. The positions of the sun and moon are known. The geometry is fixed. the physics does not change. And so the tides, for all their power and drama, are among the most predictable things in nature. There is something deeply calming in that. The ocean is vast and wild and full of force, but the forces that shape its rhythm follow rules. They follow patterns. They repeat. And in that repetition, across all of time, the sea has been keeping its own kind of clock. That clock has been running for a very long time. Long before humans had words for the sea, the tides were already rising and falling along every shore on Earth. Ancient people noticed. They had to. Their lives depended on it. The earliest known written records of tidal observation come from China, more than 2,000 years ago. Sailors and fishermen along the Chinese coast kept careful notes about when the water rose and when it fell. They tied the rhythm of the tides to the moon, even without knowing the physics behind it. They simply watched. They recorded. And over generations, the pattern became clear. The ancient Greeks noticed it too. A Greek explorer named Pytheas sailed north toward Britain around 325 BCE and wrote about tides far larger than anything he had seen in the calmer Mediterranean Sea. He connected the tides to the moon. He was right, though the full explanation would not come for nearly 2,000 more years. His observations were so surprising to other Greeks that many of them did not believe him. The Mediterranean has very small tides, sometimes just a few inches. Pytheas had traveled to a world where the sea moved in ways that seemed almost impossible. That difference between the Mediterranean and the open Atlantic is real, and it still holds today. Stand on a beach in Greece, and the tide might rise and fall less than a foot. Travel to the coast of Brittany in northwestern France, and the same moon will pull the same ocean up and down by 30 feet or more. The shape of the basin, the depth of the water, the angle of the coastline. All of these things shape how the tidal signal expresses itself. The moon gives the instruction. The ocean interprets it in its own way, depending on where you are standing. For medieval sailors, understanding tides was not a matter of curiosity. It was survival. A ship trying to enter a harbor at low tide could run aground on rocks or mud and be lost. A ship that timed its arrival with the high tide could glide in safely over the same hazard. Tide tables, written charts showing the predicted times of high and low water, became some of the most valuable documents a port could own. Monks in England were recording tidal predictions as far back as the 8th century. The Venerable Bede, a monk and scholar, wrote about the tides around 725 CE and described how the moon governed their timing with remarkable accuracy for his era. Picture what those medieval shorelines looked like. Wide, flat beaches of gray sand exposed at low tide, stretching far out from the cliffs. Tide pools left behind in the rocks, glittering and still, filled with small crabs and sea anemones and strands of dark green kelp. Then, hours later, the sea returning, quietly at first, a thin sheet of white foam creeping across the sand, then deeper water, moving faster, filling the pools, covering the rocks, rising up the face of the cliffs until the beach was gone entirely. The same beach, transformed twice a day, every day, without pause. This visual rhythm shaped entire cultures. Fishing villages built their lives around the tidal clock. Farmers in coastal areas used the low tide to harvest shellfish from mudflats. Builders learned to work on sea walls and harbor structures only during the hours when the tide was out. The tides were not a background detail. They were a central fact of daily life, as reliable as sunrise. Isaac Newton gave the world the first true mathematical explanation of tides in 1687. In his great work, the Principia, he showed that the moon's gravity was the driving force, and he laid out the geometry of how the two bulges form on opposite sides of Earth. It was a profound moment. Something ancient sailors had observed for thousands of years finally had a precise physical explanation. The mystery did not disappear. It deepened into something even more wonderful. After Newton, the science of tides grew steadily more detailed. In the 1800s, the British scientist William Thomson, later known as Lord Kelvin, built a mechanical tide-predicting machine. It used gears and pulleys to calculate the combined effect of many different tidal cycles at once. You could turn a handle, and the machine would draw out a curve showing the predicted tides for an entire year at a given port. It was one of the first analog computers ever built, and it worked beautifully. The machine is gone now, replaced by software. But the tides it predicted are still arriving on schedule. The same rhythm Pythias marveled at. The same pull the Chinese sailors mapped. Still running, still keeping time. The tides have been arriving for billions of years. And all that time, they have been doing quiet, patient work on the land itself. When you stand at the edge of the sea and look at a rocky cliff, or a wide sandy beach, or a jagged inlet carved into the coast, you are looking at the result of that work. Tides did not build these places alone, but they shaped them in ways that run very deep. The most direct thing tides do to coastlines is move material. Every time the tide comes in, it carries water loaded with sand, silt, and tiny broken pieces of shell and rock. Every time it goes out, it pulls some of that material back. This back and forth motion, repeated twice a day for millions of years, sorts and shifts the sediment along the shore. It decides where sand piles up and where it gets swept away. It is slow. It is relentless. And the results are enormous. Tidal flats are one of the clearest signs of this process. These are wide, gently sloping areas of soft mud and sand that sit exposed at low tide and submerged at high tide. They form in sheltered bays and estuaries where the water moves slowly enough to drop its load of fine particles. Over time, those particles build up into thick, layered beds of sediment. Some tidal flats are only a few feet wide. Others stretch for miles. The Wadden Sea, along the coasts of the Netherlands, Germany, and Denmark, is one of the largest tidal flat systems on Earth. It covers more than 4,000 square miles. Scientists have found sediment layers there that go back thousands of years, each one a record of the tides that built it. Estuaries are another place where tidal forces leave a strong mark. An estuary is where a river meets the sea, and the tides push and pull at that meeting point constantly. The mixing of fresh river water and salty ocean water creates a very specific kind of environment, shaped in large part by by the rhythm of the tides. The tidal flow determines how far salt water pushes upstream, how sediment settles, and how the channel shifts over time. Many of the world's great ports sit inside estuaries, partly because the tidal flushing keeps the water moving and the channels from silting up too quickly. In places where the tidal range is very large, the carving effect on rock becomes visible and dramatic. The Bay of Fundy on the eastern coast of Canada has the highest tides on Earth. The water there rises and falls by as much as 56 feet between low and high tide. That is roughly the height of a 5-story building, moving twice a day. The sheer weight and force of that much water, surging in and draining out, has carved the sandstone cliffs along the bay into extraordinary shapes. Tall, narrow columns of rock called hoodoos stand along the shore, left behind as the softer rock around them eroded away. The tides sculpted them slowly, one wave at a time. Even coastlines far from dramatic cliffs show the tidal signature. Sandy beaches are shaped by the swash zone, the area where waves run up and back across the sand. The height and reach of that zone changes with the tide. At high tide, waves reach further inland. At low tide, a wide band of wet sand is exposed. Over time, this daily shifting sorts the sand by grain size, smooths the beach face, and builds up subtle ridges called berms. A berm is a low, flat shelf of sand just above the high tide line, built up by wave action over many tidal cycles. Most beachgoers walk across one without ever noticing it. Beneath the surface of the water, tidal currents carve the seafloor too. Strong tidal flows scour channels through soft sediment and pile sand into underwater ridges called tidal sand waves. These features can be dozens of feet tall and stretch for miles. They shift slowly over time as the currents push them along. Ships navigating shallow coastal waters have to account for them, because a channel that was safe last year may have changed shape by now. All of this, the flats, the estuaries, the carved cliffs, the sordid beaches, the shifting seafloor, is the visible record of tidal energy being spent on the land. The moon pulls at the ocean, and the ocean pulls at the earth. The coastlines we know are the result of that conversation, carried on patiently across deep time. Every inlet, every mudflat, every sea stack standing alone in the surf holds the memory of a tide that came in and went out again and again until the rock gave way. The tides do not only shape the land, they shape time itself. Every time the ocean rises and falls, something subtle happens deep inside the earth. The water moving across the seafloor creates friction. That friction acts like a very gentle brake on the planet's spin. Over millions of years, this braking effect adds up. The Earth is slowly turning more slowly. This process has a name. Scientists call it tidal friction, or sometimes tidal braking. The idea is simple. The ocean bulge that the moon pulls up on Earth does not sit perfectly in line with the moon. Because the Earth spins faster than the moon orbits, that bulge gets carried slightly ahead of the moon's position. The moon pulls back on that bulge, trying to slow it down. And because the bulge is part of the Earth, the whole planet slows with it. It is a tiny effect on any given day. The change in the length of a single day is measured in fractions of a millisecond per century. You would never feel it. You would never notice it in a lifetime, or even in many lifetimes. But the universe is patient. Over hundreds of millions of years, those tiny fractions stack up into something real. Scientists have found the evidence written in ancient rock. Certain fossils, especially corals, grow in daily and yearly layers, much like tree rings. When researchers study corals from hundreds of millions of years ago, they can count how many days were in a year back then. The number is higher than it is today. Around 400 million years ago, a year on Earth lasted roughly 400 days. Each day was only about 22 hours long. The planet was spinning faster. The tides were doing their slow work even then, pulling at the ocean, spending energy, shaving tiny slivers off each rotation. This is one of the quieter rhythms of the solar system. Not the rhythm of seasons, which plays out over a year. Not the rhythm of the tides, which plays out over hours. This is a rhythm measured in geological time, in epochs and eras, in the slow grinding of continents, and the rise and fall of whole families of life. It pulses so slowly that no living thing has ever experienced more than the tiniest fraction of one beat. The energy that tidal friction removes from Earth's spin does not simply vanish. Energy does not vanish. It has to go somewhere. Some of it becomes heat, generated deep in the ocean, and in the solid rock of the seafloor as water and crust flex and rub. This heat is very small compared to the heat coming from the sun or from Earth's own interior, but it is real and it is measurable. The ocean itself is very slightly warmer because of the tides. The rest of that energy gets transferred outward. It flows through the same gravitational connection that causes the tides into the moon's orbit. As Earth loses rotational energy, the moon gains orbital energy. And when an orbiting body gains energy, it does something that feels backward at first. It moves farther away. The moon is slowly drifting outward from the Earth, pushed by the very energy that the tides steal from our spinning planet. These two things, Earth slowing down and the moon moving away, are not separate events. They are the same event, seen from two different places. They are two sides of one exchange. The Earth gives, the moon receives, and the whole system slowly settles toward a quieter state. There is a name for that quieter state too. Scientists call it tidal locking. It is the end point of tidal friction, the place the system is moving toward, though it will take an almost unimaginable span of time to get there. In a tidally locked system, one body always shows the same face to the other. The moon has already reached this state with Earth. It spins once for every orbit it completes, which is why we always see the same side of the moon from Earth. The moon's own tidal friction, caused by Earth's gravity pulling on the moon long ago, brought it to this still and steady place. Earth is on the same path, very slowly, across billions of years. The Earth's day will grow longer and longer. The tides will keep doing their patient work. The ocean will keep rising and falling, keep dragging against the seafloor, keep whispering that same slow message to the spinning planet beneath it. The coastlines record the tides in stone, but time itself carries a different record, written in the lengthening of days, in the drifting of the moon, in the quiet and steady unwinding of Earth's ancient spin. drifting away from Earth. Right now, as you read this, as the tides rise and fall along every shore on the planet, the moon is moving a little farther from us. Not fast, not in any way you could see or feel, but steadily, measurably, year after year, the moon pulls back from Earth at a rate of about 3.8 centimeters per year. That is roughly the speed at which your fingernails grow. It sounds small, and in any single human lifetime, it is. But the universe works in deep time, and small things done patiently for billions of years add up to something vast. The reason the moon is drifting comes directly from what the tides do to Earth's spin. The previous section described how tidal friction slows the Earth down, just slightly, with every passing year. That slowing does not simply vanish. Energy does not disappear. It has to go somewhere. And where it goes is outward, into the moon's orbit. As Earth loses a little rotational energy to the tides, that energy transfers to the moon. The moon absorbs it and responds by moving into a slightly wider, slightly larger orbit around Earth. The two bodies are locked in this slow exchange, this quiet negotiation that has been going on for billions of years. Scientists have been able to measure this drift with remarkable precision. During the Apollo missions, astronauts placed small reflective panels on the lunar surface. These panels, called retroreflectors, bounce laser beams sent from Earth directly back to their source. By timing how long the light takes to travel there and back, scientists can measure the distance to the moon with extraordinary accuracy. Those measurements, taken over decades, confirm it clearly. The moon is retreating. The distance grows. The exchange continues. When the moon first formed, roughly 4.5 billion years ago, it was much closer to Earth than it is today. Scientists believe it may have been as close as a quarter of its current distance, perhaps even closer. Back then, the tides it raised on Earth would have been enormous, far taller, and more powerful than anything the modern ocean experiences. The young Earth was a wilder place, spinning faster, its days much shorter, its oceans churned by tidal forces that would be almost unrecognizable today. Over billions of years, the moon drifted outward, the tides calmed, and Earth's spin slowed to the familiar rhythm we is something quietly moving about this. The moon and Earth have been in conversation for longer than complex life has existed on this planet. Every tide that ever rolled across an ancient shore was part of that conversation. Every grain of sand shifted by a retreating wave. Every coastline carved by the patient pull of the sea. Every creature that ever timed its life to the rhythm of high and low water. All of it was shaped by this slow drift, this gradual pulling apart of two worlds that have been partners since the solar system was young. The moon is not the only neighbor affected by this kind of drift. Across the solar system, similar exchanges play out between moons and their planets. Phobos, the small and battered moon of Mars, is actually moving in the opposite direction. It orbits so close to Mars and so quickly that tidal forces are pulling it inward rather than pushing it out. Scientists believe Phobos will eventually spiral close enough to Mars that the planet's gravity will tear it apart, perhaps forming a thin ring of debris around the red planet. Every system finds its own path through this gravitational dance. Back at Earth, the drift of the moon has one more consequence worth holding in mind. As the moon moves farther away, its apparent size in our sky shrinks, very slowly, over immense spans of time. Today, the moon and the sun appear almost exactly the same size when seen from Earth, which is why total solar eclipses are possible. The moon fits almost perfectly over the sun's face, blocking its light and revealing the glowing outer atmosphere called the corona that surrounds it. This near-perfect match in apparent size is a coincidence of the present moment in Earth's long history. In the deep past, the moon appeared larger. In the far future, it will appear smaller, and total solar eclipses, as we know them, will no longer be possible. The moon is leaving slowly and gently, the way all things in the universe shift and change across time. But it is not gone. It is still there, still pulling the oceans, still shaping the tides, still holding Earth in its quiet, gravitational embrace. The drift is real, but so is the bond. That bond between Earth and Moon has done something else, something that touches every single day of your life. even if you have never once thought about it. The moon's slow drift outward is connected to a change in time itself, not in the way clocks work, but in the actual length of a day on Earth. The day is getting longer, and it has been getting longer for billions of years. Right now, a day on Earth lasts 24 hours. That feels permanent, like a fixed feature of the world. But it is not. Earth's rotation is slowing down, very gradually, because of the same tidal friction discussed in the last section. The ocean tides drag slightly against Earth's spin, like a hand pressing gently on a spinning top. Over millions of years, that gentle drag adds up to something remarkable. Scientists can measure this slowdown. Earth's day grows longer by about 1.4 milliseconds every century. That sounds like almost nothing. But stretch that rate across deep time, and the numbers become extraordinary. Around 1.4 billion years ago, a day on Earth lasted only about 18 hours. The planet was spinning faster, completing each rotation well before the sun had time to cross a modern sky. Go back even further to the very early Earth, roughly 4.5 billion years ago, and the day may have been as short as 6 to 8 hours. The young Earth spun like a top, fast and furious, still settling from the violent collision that formed the moon. In those early days, the sun rose and set multiple times in what we would now call a single afternoon. Ancient rocks hold the memory of these shorter days. Certain layered rocks, called tidal rhythmites, preserve the record of ancient tidal cycles. The way tree rings preserve the record of seasons. Scientists have studied these rocks and counted the tidal layers, working backward through time to estimate how fast Earth once spun. The rocks do not lie. They show a world moving faster, a planet that has been steadily slowing for billions of years. Coral fossils offer another kind of record. Living corals grow daily growth rings, thin lines laid down each day like the pages of a diary. Ancient fossil corals from roughly 400 million years ago show around 400 growth rings per year. That tells scientists that the year had 400 days back then. Each day was shorter, about 22 hours, and Earth completed more of them before finishing one orbit around the sun. The year itself did not change. Earth still takes roughly the same time to travel around the sun. What changed is how many days fit inside that year. As each day grew longer, fewer of them fit. 400 days became 365, and the count is still falling slowly across time. This slowdown has shaped life on Earth in ways that are hard to fully grasp. The early atmosphere, the early climate, the early patterns of wind and ocean current, all of them were influenced by a faster spinning planet. A shorter day means faster winds, different heat distribution, different weather patterns. The Earth that early life first crawled across was a genuinely different world, spinning in a rhythm nothing alive today has ever experienced. There is something almost dizzying about this, in the quietest possible way. The length of a day, which feels like the most basic and stable thing in human experience, is actually a slow variable. It has been changing since Earth was born. It will keep changing long after we are gone. By the time the sun reaches the end of its life, billions of years from now, Earth's day may have stretched to something close to 47 of our current hours. The moon will be farther away. Its tidal grip will be weaker. But the slowing will have already done its work across the long ages before that point. There is a strange comfort in this if you let yourself feel it. The universe does not rush. It makes its changes in the smallest possible increments, spread across spans of time so vast they are nearly impossible to hold in the mind. A millisecond per century, a few centimeters per year. These are not dramatic forces. They are patient ones. And patience, it turns out, can reshape a world. The day you are ending right now, this particular 24 hours, is a moment in a very long story. Tomorrow's day will be the tiniest fraction longer. You will never feel the difference. But it is there, quiet and steady, the way the tides themselves are quiet and steady, pulling and shaping and changing everything, one gentle increment at a time. There is something worth pausing on here, something small and precise and quietly wonderful. The same slow process that is stretching Earth's day has already finished its work on the moon. The moon is no longer spinning freely. It stopped long ago, held in place by Earth's tidal grip. And because of that, we only ever see one face of it. This is called tidal locking. It happens when a moon orbits so close to its planet that tidal forces gradually slow its spin until the spin and the orbit match perfectly. The moon now takes exactly as long to rotate once as it takes to travel once around Earth. Both motions last about 27 days. So the same side always faces us. The same craters, the same dark plains, the same pale highlands, always turned toward us, always watching. Think about what that means for the other side. The far side of the moon, sometimes called the dark side, is not actually dark. It receives just as much sunlight as the near side, but it faces away from Earth at all times. For billions of years, no human eye had ever seen it. We only got our first look in 1959, when a Soviet spacecraft called Luna 3 swung around and sent back blurry photographs. What it showed surprised scientists. The far side is rougher. It has fewer of those wide, dark plains. It is more heavily cratered. The two faces of the same moon look remarkably different from each other. The moon did not always face us this way. Early in the solar system's history, the moon spun freely, just like Earth does now. But Earth's gravity pulled on the slight bulge in the moon's shape, creating a tidal drag. Over millions of years, that drag slowed the moon's spin. It slowed and slowed, the way a spinning top loses speed, until finally the rotation matched the orbit. And there it stopped, locked in place. Scientists call this the synchronous rotation state, meaning the spin and the orbit are in perfect sync. Earth's gravity did not do this alone. The moon also had to be close enough and massive enough for the process to work on these timescales. Smaller moons around distant planets can take far longer to lock. Some may never lock at all before their star burns out. What is beautiful here is that tidal locking is not rare. It is actually the natural end state for most moons in the solar system. Almost every large moon we know of is tidally locked to its planet. Phobos and Deimos, the two small moons of Mars, are both locked. The large moons of Jupiter and Saturn are locked. Even Pluto its largest moon, Charon, are locked to each other. They both keep the same face turned toward one another at all times. Scientists call this mutual tidal locking. Two worlds, each holding the other's gaze across a gap of just under 20,000 kilometers. There is a texture to this that takes a moment to fully feel. Charon, seen from Pluto's surface, never rises and never sets. It simply hangs in the sky, fixed in one spot, neither moving nor fading. And from Charon, Pluto does the same. Two frozen worlds, face to face, perfectly still relative to each other, while the rest of the universe wheels slowly around them. Our own moon will never quite reach that state with Earth. Earth is much more massive than Pluto, and the moon is much less massive than Charon relative to its partner. The forces are not balanced enough for mutual locking to happen in any reasonable time frame. Earth's spin will slow, yes, but the sun will likely end its life before Earth becomes fully locked to the moon. Still, the direction is clear. The universe tends toward this kind of stillness. Tidal forces are always working to bring spinning things into sync with the rhythms around them. It is a kind of settling, a finding of balance. The way a pendulum eventually comes to rest, and there is something deeply calming in that image. The moon, locked and still, faithfully showing us the same face it has shown every human who ever lived. Every person who ever looked up at night saw exactly what you would see tonight. The same craters near the top, the same dark patches, the same pale glow. Billions of people across thousands of years, all looking at the same face. Tidal locking made that possible. A slow, patient force working across millions of years until the moon settled into its place and stayed there. Quiet, steady, turned toward us always. That same quiet force, the one that locked the moon into its faithful stillness, reaches much farther than our own backyard. It stretches out across the solar system, all the way to the cold and distant worlds orbiting Jupiter and Saturn. And the story of how we came to understand that is itself a remarkable one. For most of human history, the moons of the outer planets were invisible. The night sky held its secrets well. Then, in January of 1610, Galileo Galilei pointed a small, handmade telescope toward Jupiter and saw something no one had ever recorded. 4 tiny points of light were moving around the giant planet. Night after night, he watched them shift position. He drew careful sketches in his notebook. He realized they were not background stars. They were moons, circling Jupiter the way our moon circles Earth. He had discovered Io, Europa, Ganymede, and Callisto, the 4 largest moons of Jupiter, now called the Galilean moons in his honor. Galileo did not know about tidal forces. That understanding would come much later. What he had done, without knowing it, was introduce humanity to a set of worlds where tidal forces would one day prove to be the dominant power shaping everything. He had simply opened the door. For the next 3.5 centuries, those moons remained little more than points of light. Astronomers could measure their orbits. They could calculate their sizes and distances. But the surfaces of those worlds were beyond the reach of any telescope on Earth. They stayed mysterious, patient, waiting. Then came the Voyager missions. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on a long, curving path through the outer solar system. Scientists had planned the mission carefully, timing it to take advantage of a rare alignment of the outer planets that would not repeat for another 175 years. The spacecraft would use each planet's gravity to slingshot forward to the next. It was an elegant piece of planning, and it worked beautifully. Voyager 1 reached Jupiter in March of 1979. What it sent back changed everything. The images arrived slowly, pixel by pixel, translated from radio signals traveling across hundreds of millions of miles of empty space. Scientists gathered around monitors and watched the moons of Jupiter come into focus for the very first time. And what they saw on Io stopped them cold. Just 3 days before Voyager 1 made its closest approach to Io, a scientist named Stanton Peele and 2 colleagues published a paper. In it, they predicted something extraordinary. They had done the math on the gravitational forces pulling at Io from multiple directions. Jupiter's enormous gravity on one side and the tugs of the other Galilean moons on the other. The competing poles, they calculated, would squeeze and stretch Io continuously. That squeezing would generate heat deep inside the moon. And that heat, they suggested, might produce volcanoes. 3 days later, Voyager 1 confirmed it. A mission scientist named Linda Morabito was processing navigation images when she noticed something strange at the edge of Io's disk. A faint, umbrella-shaped plume was rising hundreds of kilometers above the surface. It was a volcanic eruption, caught in the act. Io was not a cold, dead rock. It was the most volcanically active body in the entire solar system, and tidal forces were the reason. The prediction and the discovery arriving within days of each other was one of those rare moments in science when the math and the universe line up perfectly. Peale and his colleagues had followed the physics wherever it led, and the universe confirmed their answer almost immediately. Voyager 2 added more. When it flew past Europa, it returned images of a surface covered in long, reddish-brown cracks running across pale ice. The moon looked like a cracked eggshell. Scientists began to wonder what was happening beneath that frozen surface. If tidal forces were heating Io so dramatically, what were they doing to Europa, which sits slightly farther from Jupiter and experiences a gentler but still significant pull? The answer, scientists came to believe, was liquid water, a hidden ocean kept warm by tidal friction, sealed beneath kilometers of ice. That idea would grow into one of the most exciting possibilities in all of planetary science. But in 1979, it was just beginning to take shape. Just a question forming in the minds of researchers, staring at cracked ice in photographs taken by a spacecraft the size of a small car, drifting through the dark. What Galileo had started with a handmade lens and a notebook, Voyager had transformed into something almost beyond imagination. The tidal force was not just an Earth story. It was a solar system story, and the outer planets were only beginning to reveal how deep that story goes. Io is a small world. It fits comfortably inside the boundaries of the continental United States. And yet, it holds a record that no other body in the solar system can claim. Io is the most volcanically active place we have ever found. Not just active, relentlessly, almost violently active. At any given moment, hundreds of volcanoes are erupting across its surface. Some of them shoot plumes of sulfur and gas more than 300 kilometers into the sky. That is nearly 3 times the height at which the International Space Station orbits Earth. The surface of Io looks like nothing else in the solar system. It is covered in shades of yellow, orange, red, and white. Those colors come from sulfur compounds deposited by constant eruptions. The ground shifts and renews itself so quickly that Io has almost no impact craters. On most solid worlds, craters build up over billions of years. They are a record of everything that has ever struck the surface. But on Io, fresh lava buries each new crater almost as soon as it forms. The surface is being constantly repaved. Scientists estimate that Io deposits several centimeters of new material across its entire surface every single year. All of this volcanic fury comes from tidal forces. Io orbits very close to Jupiter, the largest planet in the solar system. Jupiter's gravity is immense. It pulls on Io with enormous strength. But Io is not alone in its orbit. 2 other large moons, Europa and Ganymede, orbit Jupiter farther out. Their gravity tugs on Io as well. These competing pulls keep Io locked in a slightly oval-shaped orbit rather than a perfect circle. That matters enormously. As Io moves closer to Jupiter in its orbit, Jupiter's gravity squeezes it. As Io swings farther away, the squeeze relaxes. This constant flexing, happening over and over again with every orbit, generates tremendous heat deep inside the moon. The same principle applies to bending a metal wire back and forth rapidly. The wire grows warm. Io grows molten. This process is called tidal heating, and Io is its most extreme example anywhere we have looked. The heat produced inside Io is so intense that it melts rock from the inside out. That molten rock, called magma, pushes upward through the crust and erupts at the surface. Some of Io's volcanic features are enormous. Loki Patera is a volcanic depression, a kind of lava lake that spans more than 200 kilometers across. It periodically brightens as fresh lava overturns the cooler crust, floating on top. Scientists can track this brightening from telescopes on Earth. Watching a volcano on a moon more than 600 million kilometers away change and pulse in real time. Here is the part that surprises most people. Io was not expected to be volcanic at all. Before Voyager 1 arrived in 1979, scientists assumed Io would look something like our own moon. Cold, cratered, geologically dead. The prediction of volcanic activity made just days before Voyager's closest approach was considered a long shot. When the images came back showing active plumes rising from the surface, researchers were stunned. One scientist described the moment as one of the most shocking discoveries in the history of planetary exploration. A moon the size of a small country, burning from the inside out, powered entirely by the invisible pull of gravity. What makes this even more striking is that Io has no internal heat source of its own in the way Earth does. Earth holds heat left over from its formation and from the slow decay of radioactive elements deep in its core. Io's interior should have cooled long ago. It is tidal friction alone that keeps it alive. Jupiter's gravity is the engine. The competing tugs of Europa and Ganymede are the throttle. And Io is the result. A world that should be quiet and frozen is instead the loudest, most restless place in the solar system. There is something quietly astonishing in that. A force we experience gently on Earth every time the tide rises and falls. A force so familiar that ancient sailors used it to navigate is the same force that tears open the interior of a distant moon and fills its sky with sulfur plumes. The scale changes. The physics does not. Gravity reaches across hundreds of millions of kilometers and squeezes a small world until it glows. And that same force, working more gently on Europa, just a little farther out, does something entirely different. Something quieter. Something that may, in its own way, be even more remarkable than rivers of lava and plumes reaching toward the stars. Europa is a small moon. It is about the size of our own moon. From a distance, it looks almost peaceful, a smooth, pale sphere wrapped in a shell of bright white ice, crisscrossed with long reddish-brown lines like cracks in an old painting. It is one of the most beautiful objects in the solar system, and beneath that frozen surface, something extraordinary is happening. Scientists believe Europa holds a liquid ocean beneath its ice, not a small pocket of water, but a true global ocean, a shell of salt water that wraps all the way around the moon, sitting beneath ice that may be tens of kilometers thick. Some estimates suggest Europa's ocean holds more liquid water than all of Earth's oceans combined. That is a remarkable thought. A moon smaller than our own, circling a planet hundreds of millions of kilometers away, may carry more water than the entire blue world we call home. The question that scientists puzzled over for years was simple. Why is it liquid at all? Europa sits far from the sun. The sunlight that reaches Jupiter's moons is weak and pale, only a small fraction of what warms our own planet. By every simple calculation, Europa should be frozen solid all the way through. A cold, dead ball of ice drifting in the dark. But Europa is not frozen solid, and the reason is the same force that fills Io's sky with sulfur plumes. Tidal friction is the answer. Europa orbits Jupiter in a path that is not perfectly round. It is slightly oval-shaped, what scientists call an elliptical orbit. This means Europa is sometimes a little closer to Jupiter and sometimes a little farther away. As it moves closer, Jupiter's gravity squeezes it harder. As it moves farther, that grip relaxes. This constant squeezing and releasing, happening over and over, every orbit generates heat deep inside the moon. Not the volcanic fury that tears Io apart, but something gentler. A slow, steady warmth. Enough warmth to keep water liquid in the dark beneath the ice. This is the connection that makes Europa so astonishing. The same gravitational force that creates the tides on Earth, that pulls the ocean up toward the moon and sends waves rolling across beaches, is also reaching across the solar system and warming the interior of a distant moon. The physics is identical. Only the scale and the setting are different. On Earth, tidal friction is slowly stealing a tiny bit of energy from our planet's spin. On Europa, that same process is quietly keeping an ocean alive, ocean may not be empty. Scientists have found strong evidence that Europa's ocean sits in contact with a rocky seafloor below. On Earth, the places where ocean water meets hot rock deep beneath the sea are called hydrothermal vents. These vents release heat and minerals into the water. Around them, entire ecosystems thrive: tube worms, shrimp, bacteria, all living without any sunlight at all, powered entirely by the heat of the earth itself. Life found a way to exist in the deepest, darkest places on our own planet, far from the sun, fed only by the warmth of the rock below. Europa may have the same conditions: liquid water, a rocky floor, a source of heat, the basic ingredients that life, as we understand it, seems to need. Scientists are careful to say that this does not mean life is there, but it means the possibility cannot be ruled out. And that possibility exists entirely because of tidal forces. Because Jupiter is massive, because Europa's orbit is slightly oval, because gravity, working patiently across space, generates just enough heat to keep water from freezing. There is a quiet elegance in how these systems connect. The moon pulls Earth's oceans. The sun adds its own gentle tug. And far out in the cold dark, beyond the asteroid belt, Jupiter pulls on its moons in the same way, with the same invisible force, producing something entirely different, not tides on a beach, but warmth in a hidden sea. Europa also shows signs of activity on its surface. Those long reddish-brown lines crossing the ice are thought to be places where the ice shell has cracked and refrozen, stained by minerals rising from below. The Hubble Space Telescope has even detected what appear to be plumes of water vapor venting from Europa's surface, like geysers rising through the ice into space. If that is true, then Europa is not just a frozen world sitting quietly in the dark. It is breathing, slowly, gently, releasing water into the void above it. All of it powered by gravity. All of it connected to the same force that moves the sea. Gravity does not only warm hidden oceans and crack frozen shells. It can also tear things apart. And when it does, something remarkable can happen. The broken pieces do not simply fall away into darkness. They spread out one of the most beautiful sights in the solar system. Saturn's rings are the most famous, wide, bright, made of billions of pieces of ice and rock, ranging in size from tiny grains to chunks as large as a house. From a distance, they look like a solid disk of pale light wrapped around the planet. Up close, they are a swarm of individual pieces, each one orbiting Saturn on its own path, all of them moving together in a slow, silent procession. For a long time, scientists wondered where those rings came from. One answer points directly to tidal forces. When a moon or a comet or any large body drifts too close to a massive planet, the planet's gravity does not pull on that object evenly. It pulls harder on the near side than the far side. That difference in pull, that tidal force, can become so strong that it overcomes the internal gravity holding the object together. The object begins to stretch. Then it cracks. Then it breaks apart entirely. The pieces scatter into orbit around the planet, and over time, they spread into a ring. This process is not just a theory. Scientists believe it has happened many times across the solar system and may still be happening today. Saturn's rings are thought to be relatively young in cosmic terms. Evidence suggests they formed somewhere between 10 million and a few 100 million years ago. That sounds like a long time, but the solar system is 4.5 billion years old. On that scale, Saturn's rings are almost new. Something came too close. Tidal forces tore it apart, and the pieces became the rings we see today. The rings are also changing right now. Saturn's gravity is slowly pulling ring material down into the planet's atmosphere. Scientists call this process ring rain. Tiny charged particles from the rings follow Saturn's magnetic field lines and fall inward, entering the upper atmosphere in a thin, steady drizzle. Measurements from NASA's Cassini spacecraft, which orbited Saturn for 13 years before its mission ended in 2017, suggested that Saturn is losing its rings at a surprisingly fast rate. At the current pace, the rings could be gone within a few 100 million years. What tidal forces helped create, gravity is slowly pulling back. Other planets in our solar system have rings too, though none as grand as Saturn's. Jupiter has a faint, dark ring system, made mostly of dust knocked off its inner moons by meteorite impacts. Uranus has narrow, dark rings that were only discovered in 1977. Neptune has rings as well, with bright clumps of material in them that scientists call ring arcs. Each of these systems tells a slightly different story about how tidal forces and gravity shape the space around a planet. Mars may once have had a ring too. Scientists think that Phobos, one of Mars's two small moons, is slowly spiraling inward toward the planet. Tidal forces are pulling it closer at a rate of about 6 feet every 100 years. In roughly 40 to 50 million years, Phobos will cross the point where tidal forces become too strong for it to hold together. It will break apart, and Mars, which currently has no rings, may gain them. A moon will die, and from its remains, something new will form. There is something quietly moving about that. The same force that raises the tide on a beach, that warms Europa's hidden ocean, that has slowly pushed our moon farther away. That same force will one day pull Phobos to pieces and scatter it into a glowing band around Mars. Nothing in the solar system stays the same. Everything is in motion. Everything is being shaped by forces that never rest. The rings of Saturn catch sunlight and scatter it in pale gold and white. They are made of ice that was once part of something larger, something that drifted too close and could not hold itself together. Tidal forces broke it apart, and what remained became one of the most striking sights in the known universe. Destruction and creation working together. One thing ends, something else begins. Gravity writes these slow stories across millions of years, patient and steady, never hurrying, never stopping. And the rings drift on, bright and silent, circling their planet in the dark. There is a boundary in space that no moon, no comet, no wandering body of rock and ice can cross safely. Scientists call it the Roche limit. It is named for Edouard Roche, a French mathematician who worked out the math in 1848. He wanted to understand exactly how close a smaller body could get to a larger one before tidal forces tore it apart. What he found was elegant and precise. Every planet has its own Roche limit. cross inside it, and gravity wins. The smaller body cannot hold itself together. It breaks. The Roche limit for Earth sits roughly 9,500 kilometers above our planet's surface. That is close. The moon orbits us at an average distance of about 384,000 kilometers. It is nowhere near that boundary. It is safe. But imagine, just for a moment, if the moon were somehow nudged inward, closer and closer, until it crossed that invisible line. Earth's gravity would begin pulling harder on the near side of the moon than on the far side. That difference in pull would grow stronger with every kilometer. The moon's own gravity, which holds it together, would not be enough. It would begin to stretch, then crack, then come apart entirely, spreading into a wide, flat ring of debris circling our planet. We would not be here to see it, of course, but the rings it left behind would catch the sunlight. They would glow. Depending on what the moon was made of, those rings might shine in pale gray and white, lit by the same sun that lights our mornings. They might shimmer faintly, the way ice does when light passes through it at a low angle. The moon is rich in silicate rock and some ice. Its dust and broken pieces, spread into a ring, would scatter sunlight in soft, muted tones, nothing like Saturn's brilliant bands, but beautiful in their own quiet way. This is what light does with destruction. It finds the pieces and makes them glow. Saturn's rings sit almost entirely within Saturn's Roche limit. That is not a coincidence. Scientists believe the rings formed when one or more moons drifted too close, or when a passing comet shattered a moon that was already orbiting near the boundary. The pieces spread out. Gravity flattened them into a disk, and then sunlight found them. The rings are made mostly of water ice, with some rocky dust mixed in. Ice is extraordinarily good at reflecting light. Saturn's rings reflect about 80% of the sunlight that strikes them. That is why they shine so brightly. Even a small telescope on Earth can pick them up on a clear night. A pale golden band around a pale golden planet, impossibly delicate looking from 1.2 billion kilometers away. Up close, the rings are not a solid sheet. They are made of countless individual pieces, ranging from tiny grains smaller than a fingernail to chunks as large as a house. Each piece orbits Saturn on its own path, following the same laws of gravity that govern every planet and moon. They are not touching. They are simply so numerous and so spread out in a flat plane that from a distance they look like a single glowing surface. Light plays tricks at that scale. What looks solid is mostly empty space, filled with drifting ice. The Roche limit also explains why planetary rings exist where they do, and not farther out. Beyond the Roche limit, gravity allows pieces to clump together. Moons can form. Inside it, clumping is impossible. Tidal forces keep pulling pieces apart before they can gather, so the rings stay rings. They cannot become moons. They are caught in a kind of permanent in-between state, too close to combine, too spread out to escape. Uranus has rings too, though they are much darker than Saturn's. They are made of material that does not reflect light well, possibly carbon-rich rock and dust. They look almost black against the dark of space. Neptune has faint rings as well, uneven and clumpy in places, suggesting they are young or still forming. Each ring system tells a different story about what crossed the Roche limit and when. There is something almost tender about the Roche limit. It is simply a number, a distance, a calculation. But what it describes is the exact point where a world can no longer hold itself together, where the pull from outside becomes greater than the pull from within, and what remains after that crossing, those rings of ice and rock and dust, catches the light and drifts on quietly, circling and circling, long after whatever made them is gone. Gravity breaks things apart, and then light finds the pieces and makes them shine. Gravity does not stop at the edge of a solar system. It reaches much farther than that. It reaches across the vast, cold distances between galaxies. And when two galaxies drift close enough to each other, the same tidal forces that move our oceans and heat the moons of Jupiter begin to work on something almost beyond imagining. They begin to pull at entire galaxies. Billions of stars, stretched and torn, and flung into long glowing arcs across the dark. When two galaxies pass near each other, the side of each galaxy closest to the other feels a stronger gravitational pull than the far side does. That difference in pull, that same simple principle behind every ocean tide on Earth, creates enormous tidal forces. Stars on the near side get tugged forward. Stars on the far side get left behind. Over millions of years, those differences stretch the galaxy into long, curving streams of light. Astronomers call these streams tidal tails, and they are among the most beautiful structures in the known universe. The antennae galaxies are one of the most studied examples. 2 spiral galaxies, each one containing hundreds of millions of stars, have been colliding and pulling at each other for hundreds of millions of years. Their tidal tails stretch outward like 2 enormous arms, curving away from the central chaos. Each arm is made of stars and gas and dust, flung outward by tidal forces during repeated close passes. What looks like destruction from a distance is also creation. The collision compresses clouds of gas, and new stars ignite inside those clouds by the billions. Old galaxies tear apart, and new stars are born in the wreckage. Our own galaxy, the Milky Way, is not immune to this. The Milky Way has already pulled smaller galaxies apart. The Magellanic Clouds, 2 smaller galaxies visible from Earth's southern hemisphere as faint smudges of light in the night sky, are being slowly stretched by our galaxy's gravity. A long stream of gas, called the Magellanic Stream trails behind them, across hundreds of thousands of light years. It is a tidal tale in the making, drawn out by the same forces that pull the sea toward the moon each night. Scientists can convert the gravitational signals from these galactic interactions into sound. Radio telescopes and other instruments detect the motion of gas and the intensity of radiation pouring from these colliding systems. When those signals are mapped to audio frequencies, what emerges is something low and resonant, a deep, slow rumble that seems to come from everywhere at once. It is not sound in the way we experience it, since space carries no air to carry waves, but the vibrations are real, and when instruments translate them, they carry the weight of something enormous and ancient. There is a particular kind of gravitational wave, a slow ripple in the fabric of space itself, that forms when 2 massive objects orbit each other over millions of years. Supermassive black holes, the kind that sit at the centers of large galaxies, sometimes form pairs after two galaxies merge. As they spiral slowly toward each other, they send out gravitational waves so low in frequency that a single wave can take years to pass a given point. Scientists call this the gravitational wave background, and it hums through the universe constantly, a deep and patient signal woven through everything. In 2023, researchers announced they had detected evidence of this background hum using pulsar timing arrays. Networks of rapidly spinning stars used like cosmic clocks. The signal was there, faint but real. A sound the universe has been making for billions of years. Tidal forces between galaxies also help shape what galaxies look like. The graceful spiral arms of a galaxy, like the Milky Way, are partly the result of tidal interactions with neighboring galaxies over billions of years. Density waves move through the disk of stars, and tidal tugs from outside help organize those waves into the sweeping curves we see. The shape of a galaxy carries the memory of every close encounter it has ever had. Everything connects. The moon pulls the sea. The sea's friction slows the earth. The earth drifts a little in response, and out across distances that make the solar system seem like a small room. The same mathematics plays out on a scale that takes the breath away. Galaxies pull at galaxies. Stars stream outward in long glowing arcs. New suns ignite in the compressed gas of ancient collisions, and through it all, a low, slow hum moves through the structure of space itself, patient and steady. The deep resonance of gravity doing what gravity has always done, reaching across every distance, touching everything. The ground beneath your feet is moving right now, not in a dramatic way, not in a way you could ever feel, but the solid rock of the Earth's crust rises and falls every single day, pulled gently upward by the same force that lifts the ocean. This is called the solid earth tide, and it is one of the quietest, most elegant facts in all of geophysics. When most people think about tides, they picture the sea, water rushing in, water pulling back, the smell of salt and the sound of waves. But the ocean is not the only thing the moon is pulling on. The moon pulls on everything: rock, soil, the deep layers of the planet. The entire Earth flexes very slightly, like a slow breath drawn in and then released. The numbers here are small but real. The solid ground beneath your feet rises by as much as 55 centimeters, roughly 20 inches, during a strong tidal cycle. That is nearly 2 feet of vertical movement in solid rock. It happens twice a day, just like the ocean tides, and then the ground settles back down, patient and quiet, as the moon moves on in its orbit. Scientists measure this movement with instruments called tilt meters and strain meters, devices so sensitive they can detect the bending of rock across a wide region. These instruments sit deep underground, shielded from vibration and temperature change. They record the slow, steady deformation of the crust as the moon passes overhead. The signal is clean and predictable. It follows the same mathematics as the ocean tide because it is driven by the same force. What makes this beautiful is how precisely it can be predicted. The solid Earth tide follows a pattern so regular that scientists can calculate exactly how much the ground will move at any location on Earth, at any moment in time, years, or even centuries in advance. The math is not complicated in its structure. It flows from Newton's law of gravity, from the known mass of the moon, from the known distance between the Earth and moon, and from the elastic properties of rock. Feed those numbers in, and the answer comes out clean. This is what the directive for this section means when it calls the universe elegant. The same equation that describes a falling apple describes the breathing of a continent. The same ratio of masses and distances that governs the ocean tide governs the flexing of granite. The universe does not use different rules for different scales. It uses one set of rules, written simply, and applies them everywhere. The solid Earth tide also affects something very practical: particle accelerators, those enormous rings of tunnels where scientists smash atoms together to study the building blocks of matter, must account for the solid Earth tide in their calculations. The Large Hadron Collider near Geneva, Switzerland, is a ring nearly 27 kilometers across. As the ground flexes with the tidal cycle, the shape of that ring changes by tiny amounts. Scientists must correct for this in real time, or the beams of particles inside will drift off course. The moon's pull reaches into the most precise experiments human beings have ever built. GPS satellites also feel this effect. The ground stations that anchor the GPS network shift, position slightly as the crust flexes. Engineers who design these systems must include solid Earth tide corrections in their software. Without those corrections, your phone's map would be off by centimeters. Small, yes, but in precision navigation and in science, centimeters matter enormously. There is something deeply satisfying about this. The moon is roughly 384,000 kilometers away. It has no engine, no intention, no awareness of what it does, and yet its gravity, following a rule that can be written in a single line of mathematics, reaches across that vast distance and moves the ground under your feet, bends the tunnels of the world's most powerful machines, and shifts the coordinates of every GPS station on the planet. All of it quietly, twice a day, every day, without pause. The solid Earth tide is also a reminder that the Earth is not rigid. It is elastic. It bends. It stretches. It recovers. The planet behaves more like a very stiff rubber ball than a block of stone. This elasticity is part of what allows the Earth to absorb tidal energy without cracking apart. The rock gives a little, and in giving, it endures. The ground breathes. The numbers describe the breath exactly, and the same gravity that pulls the tide across the open ocean reaches down through the seafloor, through the mantle, through the deep crust, and lifts the very ground you stand on gently, without a sound, in perfect agreement with the math. That same quiet pull that lifts the ground also moves the ocean in ways that reach far beyond the shoreline. The tides do not simply rise and fall and disappear. They push. They stir. They drive enormous rivers of water through the deep sea. And those rivers carry heat from one part of the planet to another. Without tides, the ocean would be a very different place. And without a very different ocean, the climate we live inside would not exist. The ocean is not still. It is full of currents those great slow rivers of seawater that flow through the depths and along the surface. Some of these currents are driven by wind. Some are driven by differences in temperature and salt. But tides play a role too, and it is a larger role than most people realize. When tidal water pushes against underwater ridges and the edges of continents, it creates turbulence. That turbulence mixes the ocean vertically, pulling cold, deep water upward and pushing warm surface water down. Scientists call this tidal mixing, and it is one of the engines that keeps the ocean from going still. Tidal mixing matters because the deep ocean is cold and full of nutrients, while the surface ocean is warm and often nutrient poor. When tides stir these layers together, they carry food upward into sunlit water, where tiny plants called phytoplankton can use it. Phytoplankton are the base of almost every ocean food chain. They are also one of the planet's great absorbers of carbon dioxide. Tides, in this way, help regulate what lives in the sea, and what lives in the sea helps regulate the air we breathe. The connection goes deeper still. The ocean has a great slow circulation pattern that scientists sometimes call the global conveyor belt. Warm water near the surface flows from the tropics toward the poles. As it cools, it becomes denser and sinks. Then it flows back along the seafloor toward the equator, where it slowly rises again. This circulation carries enormous amounts of heat. It is part of why Europe stays warmer than it otherwise would, given how far north it sits. Tidal mixing helps drive this circulation by stirring the layers of the ocean and allowing cold, deep water to rise back toward the surface. Without that stirring, the conveyor belt would slow, and a slower conveyor belt would mean a colder, less stable climate. The precision here is striking. The moon sits at just the right distance to produce tides strong enough to mix the ocean without tearing it apart. If the moon were much closer, tidal forces would be so strong they would create chaos in the ocean and on land. If the moon were much farther away, tidal mixing would weaken. The conveyor belt would slow, and the steady warmth that many parts of Earth enjoy would begin to fade. The distance the moon holds right now, roughly 384,000 kilometers, produces tides that are powerful enough to do real work, but gentle enough to let the system stay balanced. Earth's distance from the sun adds another layer to this balance. The sun provides the energy that warms the ocean surface and drives the winds that push surface currents. Tides and wind and solar heat all work together, each one contributing to the circulation that keeps the planet's temperature livable. Move Earth a little closer to the sun, and the ocean grows too warm. Move it a little farther, and the surface begins to freeze. The habitable zone, that narrow band of distance where liquid water can exist on a planet's surface, is not very wide. Earth sits inside it, and the tides help it stay there by keeping the ocean in motion. The atmosphere plays its part too. Earth's thin layer of air holds just enough heat to keep the surface warm at night, and lets just enough energy escape to keep it from overheating during the day. Tidal forces even act on the atmosphere itself, creating tiny atmospheric tides, small pressure waves that travel around the planet twice each day. These waves are too small to feel, but they are real, and they are part of the same system, the same set of forces, all pulling and pushing in quiet agreement. What is remarkable is not any single piece of this. It is that all of it works together. The moon at its exact distance, the sun at its exact distance, the ocean at its exact depth and salinity, the atmosphere at its exact thickness, tides mixing the water, currents carrying the heat, phytoplankton feeding on the nutrients that tides bring upward. Every part of this system depends on every other part. Change one variable by enough, and the whole thing shifts. The fact that it has held together, steady and self-correcting, for billions of years, is one of the quieter wonders of this world. And yet, for all that we understand about tides, one of the deepest questions they touch remains open. Scientists still debate exactly how life began on Earth. And tides, it turns out, may have played a quiet but important role in that story. Life on Earth started somewhere between 3.5 and 4 billion years ago. We know this from ancient fossils and chemical signatures locked inside very old rocks. But the exact place where life first sparked into being, that is still one of science's great unsolved puzzles. Some researchers believe it happened in deep ocean vents, where hot water rises through cracks in the seafloor. Others believe it happened somewhere much closer to the surface, in shallow pools along the shore. And those shallow pools, of course, are shaped by tides. The idea is called the tidal pool hypothesis. It suggests that life may have begun in small pools of water along ancient coastlines. These pools would fill with seawater at high tide, then slowly dry and concentrate as the tide pulled back. Then they would fill again. This cycle of filling and drying over and over could have helped simple chemical compounds grow more complex. Water brings molecules together. Drying concentrates them. The cycle repeats. And over millions of years, something remarkable may have emerged from that rhythm. The chemist Charles Darwin hinted at this idea long ago. He imagined a warm little pond where the first building blocks of life might have assembled. Modern scientists have expanded that idea. They have shown in laboratory experiments that the repeated wetting and drying of certain chemical mixtures can cause simple molecules to link together into longer chains. These longer chains look a great deal like the early ancestors of RNA, the molecule that carries instructions inside living cells today. Tides may have been the engine that ran this process, pulling the ocean in and out day after day for millions of years. What makes this especially interesting is that the ancient moon was much closer to Earth than it is now. Scientists believe that early in Earth's history, the moon may have been only a fraction of its current distance away. That would have made tidal forces far stronger. The tides in those ancient seas may have been enormous, sweeping far inland and then retreating dramatically. The tidal pools of that era would have been far more dynamic than anything we see today. More filling, more drying, more chances for chemistry to happen. But here is where the mystery deepens. We do not yet know for certain that this is how life began. The tidal pool hypothesis is compelling, but it is not proven. The deep ocean vent hypothesis is equally compelling. Hot water rich in minerals, rising through cracks in the seafloor, could also have provided the energy and chemistry needed to spark life. both ideas have serious scientific support. Both have gaps. The honest answer is that we do not yet know which one is right, or whether the true story involves elements of both. There is something quietly wonderful about that uncertainty. It means the question is still alive. Scientists are still searching, still testing, still finding new clues in ancient rocks and in laboratory experiments that recreate the conditions of the early Earth. Every year brings new evidence, and tides remain a serious part of that conversation. What we do know is this: life, wherever it began, needed certain conditions. It needed liquid water. It needed a source of energy. It needed a way for molecules to meet and combine and grow more complex. Tides provide all of those things in the coastal zone. They bring fresh seawater. They concentrate chemicals as the water evaporates. They stir and mix and repeat the process endlessly. Whether or not tides were the birthplace of life, they created exactly the kind of environment where life could take hold and experiment. There is also a broader thought here. The moon's gravity, which drives the tides, is itself the result of a collision. Scientists believe a Mars-sized body struck the early Earth roughly 4.5 billion years ago. The debris from that collision formed the moon. That same moon then shaped the tides. Those tides may have shaped the chemistry that led to life. A violent collision billions of years ago may have set in motion the very process that eventually produced every living thing on this planet. We cannot say that with certainty, but the possibility is there, quiet and enormous, sitting at the edge of what we know. Science is full of these open doors, places where the evidence points toward something extraordinary, but has not yet arrived. The role of tides in the origin of life is one of those doors, and it is still gently swinging open. Life did not just begin near the tides. Life learned to live by them. Every creature that calls the coast home has, over millions of years, tuned itself to the rhythm of the rising and falling sea. The tides are not just a backdrop. They are a clock. And the animals and plants that live along the shore have learned to read that clock with extraordinary precision. Consider the fiddler crab, this small, sand-colored creature lives in the mudflats and marshes where the tide comes and goes twice a day. Scientists have found that fiddler crabs carry an internal tidal clock. Even when you bring them into a laboratory far from any ocean, they still become active at the exact times when the tide would have been low back on their home beach. Their bodies have memorized the rhythm. The moon's pull is written into their biology. The same is true of the grunion, a small silver fish that lives off the coast of California. Grunion time their entire reproductive cycle to the tides. On specific nights, just after the highest tides of the month, thousands of grunion ride the waves onto the beach. The females bury themselves in the wet sand and lay their eggs. The males fertilize them. Then the fish ride the next wave back out to sea. The eggs sit in the sand, safe above the waterline, until the next set of high tides 2 weeks later washes over them. That rush of water triggers the eggs to hatch. The timing is so precise that it only works because the fish have evolved to read the lunar tidal cycle almost perfectly. Oysters do something similar. In the 1950s, a biologist named Frank Brown moved a group of oysters from the coast of Connecticut all the way to a landlocked laboratory in Illinois. At first, the oysters opened and closed their shells on the same schedule they had used back on the coast, in sync with the tides of Long Island Sound. But within 2 weeks, something remarkable happened. The oysters shifted their schedule. They began opening at the times when the tide would have been high in Illinois, if Illinois had a coast. They were responding to the faint gravitational pull of the moon overhead, even without any ocean water to feel. Their bodies were that sensitive. Plants feel the tides too. Coastal mangrove trees, those remarkable salt-tolerant trees that grow with their roots in seawater, time their seed release to the tidal cycle. Their seeds, called propagules, drop into the water at low tide. The receding water carries them away from the parent tree. When the tide rises again, it pushes the seeds into new mudflats where they can take root. The tree does not think about this. It simply follows the rhythm that millions of years of tidal living have pressed into its biology. This is one of the quieter wonders of the natural world. The moon is roughly 384,000 kilometers away. It has no eyes, no intention, no awareness of the small creatures scuttling across the mudflats below. And yet its gravity, working across that vast distance, has shaped the behavior of crabs and fish and oysters and trees. It has written itself into the DNA of coastal life. Scientists call this kind of internal biological timing a circadian rhythm. It works alongside the better-known circadian rhythm, which tracks the 24-hour cycle of day and night. Many coastal animals run both clocks at once, tracking the sun and the moon simultaneously, adjusting their behavior to the overlap between the two. Now think forward. The moon is slowly moving away from Earth. As earlier sections of this episode described, as it drifts outward, the tidal cycle will gradually change. The tides will grow weaker over millions of years. The rhythm that fiddler crabs and grunion and oysters have spent millions of years learning will slowly shift. Life will adapt, as it always has. New rhythms will emerge. New creatures will evolve to read a slower, quieter tidal clock. And on other worlds, around other stars, there may be moons pulling at alien coastlines right now. There may be creatures we cannot imagine, tuned to rhythms we have never heard, living by tidal clocks set by suns and moons we have not yet named. The same force that moves our oceans may be writing itself into the biology of worlds we have not yet found. The tides connect the moon to the sea to the shore, and the shore to every living thing that has ever learned to read the waters rise and fall. That connection runs deep. It runs all the way down into the biology of life itself. And now, after all of that, consider what the tide truly is. It is not just a force that shapes coastlines or governs the lives of crabs and fish. It is energy, raw, ancient, endlessly renewable energy. The same pull that has been slowing Earth's spin for billions of years carries within it an enormous amount of power. And humans have only recently begun to understand how to use it. The ocean holds a staggering amount of tidal energy. Scientists estimate that the tides carry roughly 3 terawatts of usable power across Earth's oceans. A terawatt is 1 trillion watts To put that in perspective, the entire world uses about 18 terawatts of energy each year in total. The tides alone could supply a meaningful share of that, if we could find ways to capture it cleanly and efficiently. The idea of using tidal power is not new. People in Europe were building tidal mills more than 1,000 years ago. These were simple wooden structures built at the mouths of rivers and bays. As the tide came in, water flowed through a gate and filled a pond. When the tide went out, the stored water was released through a wheel, grinding grain into flour. The moon was doing the work. The miller just had to be ready when the water moved. Modern tidal power works on the same basic principle, but with far more precision. One approach uses tidal barrages, which are large dam-like structures built across the mouths of bays and estuaries. As the tide rises and falls, water flows through turbines built into the barrage. Those turbines spin and generate electricity. The La Rance tidal barrage in France has been running this way since 1966. It produces enough electricity to power hundreds of thousands of homes, using nothing but the moon's gravity and the sea. Another approach uses underwater turbines placed directly in fast-moving tidal currents. These look like wind turbines, but they spin underwater. Tidal currents are far more predictable than wind. The tide follows a clock set by the moon, and the moon does not change its schedule. Engineers can know years in advance exactly when and how fast the water will move. That predictability makes tidal energy one of the most reliable forms of renewable power on Earth. The Bay of Fundy, on the eastern coast of Canada, is one of the most promising places on the planet for tidal energy. The bay's shape funnels the incoming tide into an ever-narrowing channel, amplifying it dramatically. Tides there regularly reach 15 meters, about 50 feet, from low to high. The sheer volume of water moving in and out twice a day represents an enormous amount of kinetic energy, the energy of things in motion. Researchers and engineers have been studying the bay for decades, working to find ways to capture that power without disrupting the ecosystem that depends on it. That balance matters enormously. Tidal ecosystems are rich with life. The mudflats and salt marshes that tides create are nurseries for fish, feeding grounds for birds, and filters for coastal water. Any large-scale tidal energy project must be designed carefully so that the structures do not block the movement of fish, disrupt sediment, or alter the tidal patterns that local species depend on. The engineering challenge is not just technical, it is ecological, and yet the promise is real. Tidal energy produces no carbon emissions. It does not burn fuel. It does not depend on the weather. It is driven entirely by the gravitational relationship between the Earth, the Moon, and the Sun. A relationship that has been running without interruption for over 4 billion years. Every time the tide rises, the moon is offering us something. It has been offering it since long before any human was alive to notice. Step back even further, and the picture becomes quietly astonishing. The moon formed from a collision between early Earth and a planet-sized body billions of years ago. That violent event, which could have ended everything, instead created a companion that stabilized Earth's tilt, shaped its tides, and slowed its spin to a pace that made complex life possible. And now, the same gravitational force born from that ancient collision is being woven into power grids, lighting homes, running hospitals, charging the devices that carry human voices across the world. The moon does not know it is doing this. Gravity does not have intentions, but the result is the same. A force that began in the chaos of the early solar system has become, over billions of years, something that sustains life in ways both ancient and new. The tides have always been generous. We are only now learning how to receive what they offer. And so we arrive at the end of the story, though the story itself has no end. The tides will keep moving long after tonight, long after this voice fades and sleep settles in, long after every city on Earth has gone quiet. The ocean will still be rising and falling, pulled by the same invisible thread that has connected our world to the moon since the very beginning. But what does the future of that relationship look like? Scientists have thought carefully about this, and the answer is both strange and strangely peaceful. Right now, the moon moves about 3.8 centimeters farther from Earth every single year, is roughly the rate at which your fingernails grow. It is slow, it is gentle, but it is steady. Over millions of years, that small drift adds up. The moon will keep receding, and as it does, its gravitational pull on Earth will grow slightly weaker. The tides over vast stretches of time will become a little smaller, a little quieter. At the same time, Earth's spin is still slowing down. Tidal friction, that constant, gentle braking caused by the ocean's resistance to the moon's pull, keeps shaving tiny fractions of a second off each day. A day on Earth is now about 24 hours. But hundreds of millions of years from now, a single day could stretch to 25 hours, then longer still. The change is too slow for any living thing to notice. But the math is real, and the direction is clear. Scientists believe that far in the future, billions of years from now, Earth and the moon could reach a state called tidal locking. Earth, like the moon is locked to us now, might one day show only one face to the moon. The same patch of ocean would always face it. The same mountains would always point toward it. The tides in that distant future would nearly stop. The ocean would settle into a permanent, gentle curve, held in place by gravity rather than moving through it. That future is so far away, it is almost impossible to hold in your mind. The sun will have changed long before then. In about 5 billion years, our sun will swell into a red giant, a star that expands far beyond its current size, and the inner solar system will be transformed entirely. What happens to Earth and the moon in that distant era, scientists are still working to understand. But for now, for the next hundreds of millions of years, the tides will keep their rhythm. The ocean will keep breathing. There is something deeply calming about that. The universe does not rush. Gravity does not hurry. The moon has been patient for 4 billion years, and it will be patient for billions more. Tonight, somewhere on Earth, a beach is resting under low tide. The wet sand catches the moonlight and holds it, shimmering faintly in the dark. The water pulled back slowly, the way it always does, following a schedule set by physics and kept without fail. In a few hours, it will return. It always returns. Somewhere else, a high cliff face stands above a narrow bay where the water rises 6, 8, 10 meters mergers with the tide. Right now, in the deep of night, the sea is climbing that cliff face quietly. No one is watching. The moon does not need an audience. And far above all of it, the moon itself hangs in the black, its pale surface covered in ancient craters, its near side always turned toward us, its far side always facing the stars. It has looked this way for billions of years. It will look this way for billions more. It is the most familiar object in our night sky, and it is also one of the most powerful forces in our lives, shaping our coasts, our clocks, our currents, and perhaps even the first stirrings of life itself. We live on a world that is held gently by forces larger than we can fully see. The moon pulls the ocean. The sun steadies the pull. The spinning earth pushes back just enough to keep everything in motion. Nothing is still. Nothing is separate. Every part of the system touches every other part, and has been doing so since long before the first creature ever looked up at the sky and wondered what that bright circle was. The tides will rise again tomorrow, and the night after that, and on, across a future so long it dissolves into quiet. Rest now. The ocean is still moving. The moon is still watching. The universe is still turning, slowly, gently, without end. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.